Yeah, all right, go on.
Ma'am, is there any like book or any website where we can find some kind of mathematical problems to solve? Because like there are very few problems in the assignments. So for practice, if there is somewhere we can find.
Uh, Okay, so one particular book, if you ask me, for problems only you want, right?
Yeah, for practice problems.
So these problems we ourselves create, right? So there isn't any book. If you want to look for the material, the resources for material, then Bishop is the book that is recommended by the professor.
Okay.
You might want to take a look at that. But if you want problems, solve problems, or in general problems, I mean, there won't be one particular resource as such.
But
But
like
yeah, I'll look into it. If you really want that, I'll explore, and if I find one, I'll share on discourse. Okay.
okay. Thank
Yeah,
you.
I'll try looking for
So
some good
just out,
resources. Yeah.
just to know that you said you create the problems yourself. So suppose there are numerical problems coming in quiz or graded assignments. So
Hmm.
is there any external resource as well from where we can practice beforehand? Because of the limited number of questions discussed and given in graded assignments, may not prepare to all the students, or maybe an average student like me, for the quiz. That is what I'm saying.
Yeah. So the quiz questions are actually based on the graded and practice programming assignments, right? Isn't that? Did you feel
Yes,
any
yes, I understand
difference?
that,
Yeah.
but no, instead of yeah, those were concept based questions, and really, I mean, interesting ones. So that is what I'm coming at. So if such questions are available for practice, then one will definitely practice in more more
Yeah, yeah,
scenarios.
I understand. I understand.
Yes.
So although we try to give many questions, but if you are looking for extra resources,
Like I said,
I mean, there
again,
won't be
I'll
one. Yeah.
reiterate the questions in graded assignment and the questions which come in quiz, maybe they are, very closely related, but then
Hmm.
the way they are asked and the worded, if one is practicing such kind of scenarios or questions, then one will be able to appreciate all the questions which comes in quiz as well, and it will help them.
Yeah, yeah, definitely. More problem solving helps, right, for understanding anything. So I understand your point. So if there is any good resource that I come across, I'll share it
No, like you said,
over
you
discourse.
you prepare the questions yourself. So why,
Hmm.
if it is possible for you to prepare, say,
More questions.
question bank kind of thing,
Yeah, so the questions are being gradually prepared, and that's how you're getting them, right? So
maybe if
probably,
you
you
can,
know, with time you will
if
get.
uh, course team can provide such a question bank before quiz too, that will definitely help.
So mock is something that probably can be considered, right, for quiz. That's something that we can look at. I think that would
We had,
eventually
I
help you,
I
right?
don't think we got a mock NMLT.
Yeah, because the questions were based on graded only. So I mean, we didn't create one
I
explicitly.
understand.
Okay,
That was just
but
my
if you are
request.
looking for,
That was just a point I
mm,
wanted to make. Thank you.
yeah, no problem. So we
And
understand.
I checked. If you can check the calendar till first of this month, I mean,
Mhm.
you will find three or four YouTube links in calendar are not updated.
Yeah, I made a note of that. So calendar links are missing. I understand.
Thank you.
So we'll get them added. We'll
Thank
see
you.
which ones are missing, and yeah, we'll get them added.
Yeah, I think one more point, ma'am. After the session is done, either in the live or if a tutorial can be done to solve one example with the data. Like for example, right now kernel function theoretically I understand, but with data, if you can show that one example, that
So the kernel week two, are you referring
yeah,
to, Nisha?
yeah, right. So I mean, such cases are there. Like okay, linear regression and all is fine, but
Hmm.
such a thing like for PCA or for a kernel. Those are little things. So over there, if we can show with one set of data and then say, okay, this
In
is
week 2, graded or practice, isn't there any question that uses some
It
data,
was there, ma'am.
I mean,
It
small
was there.
scale
It was
data?
discussed in the lecture also.
Live session, you mean, or
Lecture
lectures?
also, live session as well, and assignments also.
because till now I think kernel part I'm very clear on that. So the tutorials, if with data can be done, that would be really helpful.
So numericals using data, right?
Yeah, yeah.
Or you want to see using code?
Not code, not code.
Okay. All right. Using data, I think in graded and practice there are, but I think you're looking for, bigger examples, right?
Right.
See, you will need to compute eigenvalues and eigenvectors, and if the data is huge and you want to get your hands dirty, you want to do it yourself, definitely that will take even more time. So probably that's the reason there are small examples in week 2 or in any other week, because you have to do the computations yourself. So are you looking for
Not
computations on
not
big data?
not heavy computation, just to understand the whole steps.
Yeah, I understand. Steps should be clear from small data also. The only concern that I'm feeling, although I'll put this point across and we'll see what best can be done. So what I'm feeling is, if the data is huge, you will, and you want to see things in action yourself, seeing, making the computation, then it will take a lot of time for finding the eigenvalues, eigenvectors, and all other computations that are required, inverse of a matrix, whatever that is. So probably that's why small examples are taken. But nevertheless, steps can be made clear, whatever manner possible. That can be made possible using the data to whatever extent possible. So I'll put across this point, Nisha. So it's well taken. Definitely, more the practice, better the reinforcement in your minds, right?
Yes, ma'am. Thanks.
So
Like in MLF, I guess there are tutorials, right? After one things are explained for each of them. So that really helped. So in similar ways.
see, in MLF, we prepared tutorials explicitly, and yes, Nachiket, yeah. So in MLF, we saw that when we saw the data, the metadata, we saw that many students didn't even watch the tutorials, and then they would come up with the problems. There also, we had the same things, like, uh, you know, uh, they would not watch the tutorials, and then they would ask similar questions on discourse or wherever else. So anyway,
That category anyway will be there, but
yeah, that will always be there. But yeah, there is a group of set of students who did watch the tutorials in MLF. But the data said that there were very few takers. So they would watch the main lectures and not the tutorials. So that's why we thought, let it be. Anyway, we are explaining, in the form of assignments and discourse and live sessions. So this should be sufficient. But yeah, we can see what more can be provided to ease the understanding of the concepts. We will see.
yeah, thank you.
All right. All right. So how was quiz 1, everyone? So I guess it was not very difficult. Or was it?
It was, I think the marks were like 6-6. So if you get something wrong, you get, you it will go off.
Okay.
So,
Computation wise, you're
yeah,
saying.
computation
Okay.
wise, yeah.
All right. Yeah, definitely. Yes, Preeto, the solutions. See, in the end, you can just take a look at these solutions, and the concept might be clear. So, if the questions are based on the graded and practice, then definitely they are very useful for quiz preparation, at least.
And
All
I
right.
also use them
Yeah.
as kind of a formula bank because some of the questions like they had the formulas in them. So I just took a quick revision of those.
Oh, nice. Okay, that tells us that we might probably, if you're using them as sort of a question bank, we might consider putting the formulae also over there, right? So that might be helpful. In the forthcoming solutions, it might be good to have detailed solutions there if you're using them.
Regarding
Yeah.
regarding the quiz, I think there was one particular question which was like it was totally unique. I did not find that type of question either in PS or in GS, but right now I am unable to recall the exact type. So I'll get back to you on discourse. I have to ask about that actually. I could not solve
All
that
right.
question.
Yeah, sure. Which week was that in?
No, it was in quiz. So I think it was week 2 or week 3, I guess. I'll take a look at the question paper. It has been released, so I'll get back to you on discourse.
Yeah, yeah, sure, sure. All right. So another thing that we I had to bring in, uh, the how much of the coding that you people are doing. See, we are explicitly preparing programming assignments, and we assume that, see, when the programming is not there, then there is this comment that we are not seeing things in action. When programming is there, then at least you can see that you using the same formula, you're able to see the results, you can see things in action, right? But the participation, in the sense of submission of programming assignments, has been very, very low. Yeah, that's what, Preethadeep. So you're saying you didn't code at all as part of MLT. So we are preparing explicitly these assignments, and I think at the level that you can easily understand. But the submission has been quite low. So this is a little concerning. So how many of you have been submitting programming assignments in the previous weeks, if you have submitted? Okay, Nachiket. Others?
I
See,
believe the fact that it is not compulsory is the reason why most of us are not doing it as such. So
so,
at least that is the case for me. If it were
okay.
compulsory, I would have done it. But since I am already doing MLP on the side, so I didn't like bother taking a look at all of them and doing
You're
it again.
doing MLP on the side.
Yes, ma'am.
Okay.
Both MLT and MLP I took together.
Yeah,
Also
so
MLP projects, so all of them.
I see. So yeah, Sanjay, Bimlesh, you have not been doing, right? So in MLP, the next course that you will be doing, in MLP, you will be using libraries directly, and the libraries will do the job for you. At one level, it is fine. So in MLT, you are understanding the techniques, the theoretical details, and then in MLP, you will just use the libraries. But these programming assignments that we have in MLT will actually bridge the gap between your theoretical understanding and uh, the library usage in MLP later on. So I think it is important to do these assignments and submit them to whatever extent that is possible. I understand it takes extra time, and we explicitly made it optional so that those who can handle will handle, those who cannot, and they should not suffer, at least on the marks front, at least on the grades front. So that's why it was made optional. But it was actually good to have it. It would have been good to have it compulsory, so that you would have done it, because later in MLP you will not get the in-depth uh, understanding, because you will directly make use of the libraries, right? I hope you understand this. Uh, yeah, yeah, Sanjay, these are very, very important, and we are we are doing stepwise things there, uh, so that you can understand what is happening. So whatever formula is derived in the theoretical lectures by the professor, you might want to see how that formula is applied to some data, be it synthetic data or real world data, and see whether the same thing is happening or not, right? I think it is very important bridge that you should try to cover. Okay, so if you have not started, it would be a good idea to start now, and start submitting. Okay, we saw the numbers recently, and they were they were not good for programming assignments. All right, so today we will be doing coding for week 6, where we would be coding some linear regression and ridge regression, and we would see how things will change. Okay.
By any chance, we are postponing week 6
Yeah,
assignment
yeah, yeah.
deadline?
Yes, week 6 assignment deadline will be extended to 23rd. You will get an email regarding this very soon.
Thank you, ma'am.
Yeah, yeah. So you can comfortably do it, understand well, and you can do it later. Uh, variance along. So, Preethadeep, can you speak up?
Yeah, ma'am. Actually, Nachikat asked me in the chat box like which question that was. I
Okay,
was
you are
referring to a
speaking to
question.
Nachiket. All right.
Yeah, so yeah, it was that question like what is the minimum value of theta? I could not find it like that type of question in either PS or GS, so I could not solve that during the quiz.
Sorry, which week again? Which week was it referring to? Which week does it belong to, the question?
It's from the quiz actually. It is the question that like consider a centered data set of 100 points in R5, and theta was defined as
Okay.
variance along first principal component divided by sum of variances along all 5 principal components. We were asked to find the minimum value of theta.
Okay, so it might be week 2, right?
Yeah, it might be week 2, I think. Yeah.
Okay. Okay, then it would be a good idea to drop a message on discourse regarding this.
Yeah, yeah.
Okay.
Yeah, I'll post this on discourse.
Yeah, yeah, sure. All right.
Is it
So,
is it fine if I tag you there?
yeah, yeah, sure, you can do that. Yeah,
Okay, okay,
yeah.
thanks.
All right. So, let us see a few things in action. So, the most important things that you understand, that you derive in lecture videos, we convert them to code. So, here in this week, what we will do is we'll first see linear regression as usual, which you would have seen in the previous week as well. And then we will see how applying ridge regression, which means applying regularization on the weights, how it affects the weights that are produced. We'll see that visually also. So that's what we are going to do now. So this is the questions collab. Uh, these are the questions. So let's start from the beginning. And I don't know how much you know and how much you don't know. So NumPy is going to be extensively used for programming. So what I'll do is I'll start off with a few basic things which we are going to use for implementing linear regression and ridge regression, so that it becomes easier for you to understand how we are applying the formula. So of course NumPy has to be imported. So I'll import that, and we'll be plotting things. So let me import matplotlib as well. All right. So there are a few basic things, basic functions from NumPy which we will be using. So let me ask you if you know about them. If you know, please tell me, and then I'll skip the explanation. If you don't know, I'll explain that. Okay. So what does this function do? Anyone? A range, NumPy dot a range. Any idea? You can just speak up if you know, else I will anyway explain. Okay, no clue, is it? So a range, it produces some values in a given range. Okay, so the syntax of the parameters is start, stop, and step. Okay, so start means from where you want the values. Let's say from step means what should be the gap between these values. So let's say I write 2.
Excuse me, ma'am.
Yes.
Yeah, ma'am. How to ma'am do like a kind of help like np.arrange? I want to get a manual page. I forget like something question mark and enter. No, we have to do.
Okay, this thing you want to see.
Yeah. Yes. Okay. Yeah.
Okay, just put
Yeah.
a question mark. So what you can do is you can go to the documentation of numpy.arange online, but if you want to see it in the collab itself, you can put a question mark. So first you have to import numpy for that. Okay, once you import that, you put a question mark, and then you write the name of the function that you want to know more about, and you
Question
can
mark
get the
before like before that.
before that. Yes.
Yeah.
And then you get the details of the parameters, like whatever I'm just now explaining, start, stop, step, and all these things, and some examples. So all these things you can get in the collab. All right. So start from 1 and end, stop at 10, and the gap should be 2. So these kind of numbers will be generated. Let's say I make the step size to be 1, then obviously you will be getting numbers from 1 to 9. Please note in a range, the last number is excluded. Okay, so it will go up to 10 minus 1. Okay, another thing that we commonly use is the start is optional and the step is also optional. Okay, so the default value of start is 0 and the default value of step is 1. So if you skip them, you're still good to go. So let's say I pass only one value. That one value will refer to the stop. and the default value of start will be taken, which is 0, and the default value of step will be taken, which is 1. So if I do numpy dot a range, I get 10 numbers starting from 0. This is a very commonly used function. Whenever you have to implement any algorithm, any ML technique from scratch, you extensively make use of numpy functions, and numpy.a range is one that is extensively used. So if you understand this, you should also know that you can just pass one value, and that one value will mean this top value, the end point. Okay. Just one more example and I'll proceed. So can you tell me what will be the output of this? Anyone? Any guesses? Just pick up. No clue, is it?
1, 4,
Hmm.
7. Yeah,
Very good.
2 values will be.
Yeah. So 1 starting from 1 and the gap of 3, which will be 4, and then 7, and 7 plus 3 is 10, but 10 is not included. Okay. So it will stop at 7. So these are the numbers that will be produced. Okay. I hope this is clear. Now there'll be another function that we'll be using in a while, which is numpy dot random dot shuffle. And why we need to shuffle the data, I'll explain you. So for now, let's try to understand how this one works. Numpy dot random dot shuffle. What it does is it shuffles the values in an array. Okay. So let's say I create this array, assign it to A. This is array, right? 0 to 9, as we know. Now, if I shuffle this numpy dot random dot shuffle and I put A, and then I print this A again. So earlier the values were 0 to 9 in sequence. Now those values have been shuffled randomly. Okay. So this is another important function. Please note that it changes in place. In place means it will make changes in the array A itself. So there are some functions for which you would need to do A is equal to something. Right? So that means they don't make changes in place. So let's say this is some function fun, and when you call this function on this A, it will produce some result, but it will not make changes in A itself. So for that, you will need to write A is equal to function of A, because the changes that this function made were not in place. However, this numpy.random.shuffle makes changes in the array in place, which means A will be altered. Now, if you print A, it is altered. So that is the function of shuffle. Okay. Now another thing, let's say this is your A, and you have to print the first 6 values, let's say. From this array, you want to print first 6 values. What will you do? Can somebody tell me? You want to print first 6 values from this array. What would you do?
Colon 6.
Very good. Colon 6. So before colon, we've not written anything, which means start from the beginning. And the 6 means this is a slicing again. And in slicing, the last element is not included, which means it will go up to 5. So it will start from the index 0, 1, 2, 3, 4, 5. Okay. This is how you print the first 6 elements. Let's say you want the last 6 elements. What would you do? Can anybody tell me? Last 6 elements. So if I do this, element after 6 onwards. Okay, my question is, you want all the elements starting from index 6 up to in the end, up to the end. So, yeah, same way I can do 6 and then colon, and I don't write anything over here. That would indicate go till the end. It will start from the index 6. So if I do this 0, 1, 2, 3, 4, 5, 6, so it will start from this one 6, 7, 0. Okay, I hope this usage is clear. Don't get confused if I use it later on. Now let's say I have a matrix now. How do you create a matrix in NumPy? You pass a 2D list. Let's say 1, 2, 3 is the first row, and then let's say 4, 5, 6 is the second row, and then let's say this is the third row. So this is when passing to this is Rx. This is a matrix. Okay. Now, if you have to take the transpose, so we've been doing transpose, right, in the lectures. So if you are given a matrix and you have to take the transpose of it, what would you do? Anyone?
X dot T.
Yeah, you can simply write x dot p, capital T. Okay, that will transpose the matrix, which means the rows will become columns and vice versa. So this row 1 to 3 has become the column. So this is how you transpose a given matrix. If you want to create a numpy array with all ones, okay, there is a function numpy dot ones. Okay, you will pass the size of that array that you want. Let's say I pass 3 numpy dot ones. You get 3. You get a numpy array with 3 ones. Okay, this was a 1D array. So if you want a 2D array, let's say 3 cross 3 array you want with all elements 1, you might want to pass 3 comma 3. But please note, if you run like this, you'll get an error. What it expects is a tuple having the shape. So this is the tuple that we pass as the parameter, which contains 3 comma 3, which means I want 3 rows and 3 columns. So if you do this, you get a 1 cross 1 matrix. 3 cross 3 matrix with all ones. Okay. So this is something that you should know. And there's another useful operation. If you have to implement linear regression, this will be useful. So there is a function numpy.columnStack. As the name indicates, it should stack the columns. Okay. So let's say numpy.column.stack. It expects what is to be stacked. It expects a tuple of what is to be stacked. Let's say I pass two lists or numpy arrays. You can either pass lists or numpy arrays. It will be able to stack them. So let's say I pass this array, 1D array, 1, 2, 3, and then another 1D array, 4, 5, 6. And then I call numpy.columnStack. Sorry, column_stack. Not, yeah, I had written column.stack. So column_stack is a function. So what happened? This was converted to a column. This was converted to a column, and they were stacked together, one after the other. Okay. This is the result of applying numpy.columnStack. So I'll explain you in a while where this kind of operation will be required. Now here, both the things were 1D arrays. This was 1D array, this was 1D array. Now let's say the second one, one of these is a 2D array, let's say. Then what will happen? Let's see that. Couple of what has to be stacked. And the first thing that we want is this 1D array. And the second thing is a 2D array. Let's say 4, 5, 6, 7. Let's see. So this is a 2D array, which is the second thing in the tuple. Okay. So let's see what happened. So what happened? This 1, 2, 3 was converted to a column, and this is the first column. And then after that, this 4, 5, 6, 7, 8, 9. This was anyway a 3 cross 2 matrix, right? What was this? This was a 3 cross 2 matrix. You should be aware of the shapes. That is very important. So the shape of the second parameter, which is this numpy array, is how much? 3 cross 2. And that is perfectly fine because the shape of the first array is 3, which will be converted to column, will be 3 cross 1. So the number of rows in this particular matrix has to be 3 cross something. Okay. So let's say I change this the shape. Let's say I'm just giving you an example. I pass this. I'm doing is I'm passing 4, 5, 6. Let me show how it looks like. This is a matrix with shape 2 cross 3. If you pass it in column stack, you will get an error. Why? Because the shapes are not matching. That's what I'm trying to explain you. So when you do this column stacking later on, you should be aware of the shapes of what you are trying to stack. So this is going to be column, and the same shape should be there in the rows of this very matrix. Okay, so that you can keep in mind. Okay. Let me just show you one more example for stacking. I'll pass a tuple of what has to be stacked. Let's say I'm storing it, let's say, in the form of a variable. This is our matrix X, and the shape is 3 cross 2. Okay, so what I'll do is I'll create numpy dot ones with shape 3, and I want to stack it with this matrix X. Okay, something like this we'll be doing in a while. So just see it in steps. Numpy dot column stack. What I'm trying to stack, I'm trying to stack something before X. What I'm trying to stack is a column having all ones. Column having all ones. What should be the shape of this column is what we need to see. So the number of rows in X are 3. So we should have the shape of this numpy dot ones to be 3 only. Okay. Instead of this, you could also write X dot shape 0. Right? Makes sense? So when you write X dot shape, what do you get? You get the shape of X, which is equal to 3 cross 2. When you write X dot shape 0, you get the first index of the shape, first value of the shape, which is 3. So you can simply write X dot shape 0 if you don't know what is the shape of X. So this operation, I hope it is clear to everyone. And I hope you all know how to multiply two matrices, right? If there are two can anybody tell me what is the operation to multiply two matrices? Very basic question, but I hope everyone.
At the rate.
Correct. Right. So if you make use of some other operation, you'll get incorrect results. So matrix multiplication that we want in these formulae that we want to do, it expects matrix multiplication, not any other multiplication like Hadamard multiplication, which is obtained when you simply use this R multiplication sign. Anyway, so I'm creating these two matrices. So let's say the same matrices. And then I will write A at the rate B. That will give me the multiplication of these two matrices. Let me save it in some other matrix, and we'll use this matrix C. So this is our C. If you want to sum up all the elements in C, what function would you use? You want to sum up all the elements in C. Anyone?
C1 dot sum.
C dot sum, is it? Like this? C dot sum is also correct. So there are some functions which can be used two ways. You can either write C dot sum, the matrix dot sum, or you can write numpy dot sum C, numpy dot sum of C. Both are valid. Okay. So there are some functions which work these two ways. Now this was the sum of all the elements. Now let's say I want you to give me the sum of these columns, like 7 plus 15, I want you to give me, and 10 plus 22. I want a row, let's say in the bottom, which contains the sum of all these columns. Okay. If you want something like this, you can pass an axis. Axis is a very important parameter in NumPy, which you should be clear with. So if you want the sum as a row, you'll pass axis is equal to 0. Now, what did I get? 22, 32, which is 7 plus 15 and 10 plus 22. Okay. This is quite useful in various scenarios. Okay. Let's say you have marks of students and in different subjects, physics, chemistry, maths, let's say. You want, let's say, so similar to some, they can be mean also, right? They can be mean also. You might be interested in average values. So let's say you want the average that every student obtained in physics. You want the average that every student obtained in chemistry and so on. So you want a row in the bottom. So for that purpose, you might want to make use of axis is equal to 0. On the other hand, if let's say you want to get the average of all the students' marks, right? Which means you want some column wise, right? You want some column wise. So physics, chemistry, maths, marks are there, and this is student 1, student 2, student 3, like this. So if you want the average, let's say average marks in physics, average marks in chemistry and maths, so you will pass axis is equal to 0. On the other hand, if you want, let's say, average marks of student 1, average marks of student 2, and student 3. So you want sums a column wise which add up the average, find the average of all the rows. Then in that case, you will pass axis is equal to 1. So this applies to both mean and sum. So we will be computing sum of squares of errors, and there it might be useful. So if I do this, by dot sum, let's say axis is equal to 1, I'll be getting sum in a column, which is 7 plus 10, 17, 15 plus 20, 37. Okay. All right. Now, for linear regression, what is the formula for linear regression? If you want to get the weights using the normal equation method, so I hope this is clear that linear regression can be solved in two ways. One is normal equation method, and second is, tell me, anyone? No? Gradient descent method, right? Linear regression problem can be solved in two ways. One is analytical way, also called normal equation way, where we simply use an equation. What is that? X transpose inverse XY, right? This is the normal equation way to solve for linear regression, which directly gives you a vector W, which contains the weights. Okay. Now, as you can see, this involves computing inverse of a matrix, which is X transpose, where X is your feature matrix. If X is huge, so X is like this. This is X1, this is X2, and so on. And these are the features. Let's say D features. If there are D features, the size of this matrix will be D cross D, right? If there are thousands of features, this matrix will have that much shape. Okay. And if you have to use this method, you will have to compute the inverse of this huge matrix, which is, so 1000 might be probably still fine, but in practice, we might have more features. let's say 10,000 features, and finding an inverse of 10,000 cross 10,000 matrix may not be a good idea computationally if you have limited resources. So you cannot use this particular method, and you move towards gradient descent. Okay, so gradient descent doesn't use any direct equation like this. It works in an iterative fashion. Okay, I hope that is clear to everyone, right? So you start with some place and move in the negative direction of gradient and so on and so forth. That's how you reach the minimum. So currently, let's talk about this equation method. So inverse is what you have to compute. So in NumPy, how do you compute the inverse? Let's see. Well, inverse may not exist for every matrix. I hope that is known to everyone. There are some matrices, given their the kind of elements that they have, if they are linearly dependent, the inverse might not exist. And for that, we have pseudo inverse. This is pseudo inverse. So that's why we actually replace this by pseudo inverse. So let us see how we can compute that in NumPy. So NumPy has another module, linear algebra, which contains different functions for linear algebra in particular. So numpy.linalg.inv for inverse. Okay. Do we have a matrix C only? Let's take C only. So you will pass the matrix, and that will give you the this is inverse. Okay. For this matrix, the inverse existed, so we got it. If the inverse was not existing, we would have gotten an error. So in general, we can make use of this function P inverse for pseudo inverse. So if the inverse of the matrix exists, it will be same. If the inverse doesn't exist, here you will get an error, and here you will get some approximate inverse which you can continue. Okay, this is one function we'll use, and another one, identity matrix, right? I hope everybody is aware of identity matrix, where the diagonal elements are 1 and rest are 0. So this is also an important matrix which we'll be using today for solving ridge regression. So numpy.eye for I. Here you will give the shape. So it is always a square matrix and symmetrical, of course. So since it is square, you just pass one dimension, 3 cross 3, it will be. So this is the kind of identity matrix that you get. All right. Now you understood numpy.arange, right? There's one more function, a little similar, but but it is different in one parameter, which is numpy.linspace, quite extensively used. Every data scientist should know this. Numpy.linspace, it produces elements equally spaced. Okay, linearly equally spaced. So the syntax is start, stop, and then end. So the numpy.arange was start, stop, and step, the gap. Here it will be start, stop, end, how many elements you want. So let's say I pass 0, 10, and let's say 11, I write. Which means between 0 and 10, including 0 and 10, I want 11 elements. One thing to note is says this 10 is included. In arange, this 10 is not included. This is one difference if you can keep in mind, but it's okay. You can see the documentation if you don't remember. So between 0 and 10, it will produce 11 elements, including 0 and 10. Okay. Let's say I pass 10 here. So let's see what we get. We get some fraction values, but they all are equally spaced. Okay. So accordingly, it'll decide. So when you know how many elements you want to produce, you will use linspace. When you know what should be the gap between them precisely, you will use arange. Okay. Let's say I pass 20 here. So accordingly, I'll get these values. So later, those who are doing MLP also, probably you might be doing hyperparameter tuning. So there we pass several values, and linspace is a very commonly used function. Okay. All right. And just one more thing we'll see, and then we'll start off with the assignment. So Let's say I have a NumPy array, and let's say some values I'll pass. Okay. Now, if I do y0, obviously, what will I get? I'll get the first element, right? Let's say I want more than one elements. Let's say I want the element at index 0 and 0, 1, 2, 3, and index 3. What should I write, anyone? I want the elements at index 0 and index 3. Anyone? Some idea, tell me something. Shall I write like this? Is this okay?
This will give all elements between 0, 1, and 2.
Is it?
No?
That requires a colon.
Colon, yeah, right.
So if I write a colon, then whatever you said is correct. If I put a comma, if I want specifically the element at 0th index and 3rd index, shall I do like this? No. I have to pass a list of those indices that I'm interested in. Please note this. Okay. 0 and 3 only I'm interested in. So I'll write it like this. Please note this. So let's say I write 0, 1, 2, 0, 1, 2, 3. I will get 10, 40, 26, 47. If I want in some other fashion, I will get the elements accordingly. We are going to make use of this in a few minutes. I hope this is clear. So firstly, we pass a list of those indices that we are interested in, and the sequence of these indices will give us the elements in that very sequence. Okay. All right. Let's now start the assignment. So where are the questions? Okay, so we have to load the data. So see, there are various sources of data. One is we can use synthetic data. I think in the last assignment we had created data synthetically by using NumPy operations. There are some real world data. There are huge data sets also available. Apart from this, there are some toy data sets available in sklearn. So we'll code our functions ourselves, but the data we'll use from sklearn. So that's what we are going to do. So sklearn provides some data sets, and they are not very huge. So they are okay for us to experiment with. So there is a diabetes data set in sklearn, which we will be using. So the library that we need to import is from sklearn dot datasets import load underscore diabetes. It's a regression data set. So in sklearn.datasets, there are some classification data sets and some regression data sets. So this is what we will be using. Now, in order to load data, we have to create an object of this load underscore diabetes. There are various parameters of this library. Whether you want the data in NumPy array form or whether you want data in data frame, pandas data frame, right? Pandas is also very important for a data scientist. So whether you want X and Y together. So whenever we refer to data, we'll always refer to it like this, X comma Y. That's our data. Where X is our feature matrix, Y is our target column. Whether you want data separately, if you want that way, you can pass a parameter.
Return XYZ.
Return XYZ. So let's say I don't pass anything. I just simply write data is equal to low diabetes. If I see the type of data, it will be a bunch object. It's a sklearn utils bunch object, which is similar to dictionary. Don't get into this. Don't worry about it. As return x y is equal to true, and I fetch the data in the form of x and y. This is what I'll do. Now, if I see the type of x, it's a NumPy array, and same goes for y. This is how you want to proceed with. If let's say you were using some sklearn libraries later on for performing linear regression or rich regression, we might probably convert this into data frame. We might want to get this data in data frame, but here we want NumPy, so we're good to go. All right. There are some random functions we'll be using later on, so that's why we will set some seed value, which I've mentioned here, numpy.random.seed. Let's set that so that we get the same results. I'm passing the seed to be 0. Okay. Now, the first question is how many samples are there in the data? Anyone would like to tell me what to write here? No?
Shape.
Right. Yeah. X dot shape. How many? What are we asking? How many samples are there? So,
0.
X dot shape 0. Right? The number of rows. And next is how many features are there? X dot shape of 1. All right. So, there are 442 data points and 10 columns. Out of these 10 columns, one column is, no, sorry, all of these are features. Y is separate, right? Y is separate. So all these 10 are going to be our features. Okay, what are we asking next? All right, write a function shuffle data that returns the shuffled X. Why do we want to shuffle? Firstly, let's try to understand that. So those who are doing MLP might know that once we get the data, we divide this data into train, and test. So there's a library that we use, train, test, split. We use this, and this is available in sklearn.model selection. I'm just telling, don't worry about it. sklearn.model selection has this library, train, test, split, which splits the data for us. But being a data scientist, you should be able to write this function yourself. Okay, which means X and Y are given to us. We should be able to write a function to split this data, this X into X train and X test, and this Y into Y train and Y test. Okay, so this is something that we need to do before we apply any model to it. We need to prepare our data. Now, how can we do this? So what we do is, out of all the data, we keep some portion aside, which is generally some 20% or 15%, or basically 10 to 25% generally. We keep this much data aside as test data, and the remaining is used for training. Okay. Now, what we can simply do is, from all the data, first let's say 25% we want to keep aside. So first 75% we can keep in the train data, and the next 25% we can keep in the test data. Given the functions that we have just now understood, you can actually use them to do this. Now, it's actually not a good idea, because probably there is some pattern in the initial few data points which is not there in the later few data points, or vice versa, and vice versa. Okay, there could be some pattern in the later data points which is not there in the initial data points. So you want to leave out that possibility. So always it is a good idea to shuffle this data first and then divide it. Okay, you shuffle all these values, and then you take the first 75%, you take them to go to train data, and the remaining 25% will go to test data. That's a perfectly fine way. So when you use this library, there's actually it actually does this way internally. Okay, so before we divide into train and test, we want to shuffle this data. So that's what we are asking here. Write a function shuffle data that returns a shuffled X and Y. I don't know why this is not complete. The shuffled X and Y. Okay. Now, another thing to note is, whenever you're shuffling, so your data is in X and Y. Whenever you're shuffling X, the same shuffling has to be applied to Y, isn't it? Is that clear to you? So there are pairs, right? X1, Y1, X2, Y2, and so on, right? If you apply some shuffling to this X, you cannot apply a different shuffling to y's. Then the association will not exist, obviously. It's a common thing, right? So whatever shuffling you apply on x, the same shuffling has to be applied on y also, so that you get the, you basically shuffle the pairs. Well, it is not complete. I had added one more statement here. I just wanted to mention, I had mentioned that the shuffling should apply on pairs. All right, I hope that you understand now. Now we have seen this shuffle function, right? Numpy dot random dot shuffle. Okay. So what I'm saying was we have to apply the same shuffling on x and y. Okay. So what we can do is, let me write this function. Let me create this function, shuffle data. What do we want to pass? X and y. Okay. What do we want to do this in this? We have to apply some shuffling to both x and y. So let me create a list, numpy array, basically numpy dot a range of the same size that the size of x is. Let's say there are 30 elements in x. I mean, 30 cross some 10. Let's say this is the shape of x and the shape of y is 30, right? So I'll create a numpy array of 30 elements, 0, 1, 2, up to 29. Okay. And then what I'll do is I'll shuffle them. When I shuffle them, I'll get some 2, 8, 18, 20, some shuffling I get. Okay. And I choose from x these elements in this order. I choose from y these elements in this order. And that's how my x and y will be shuffled pairwise, which means whatever shuffling is applied to x, the same shuffling will be applied to y. Is this clear? Any is this clear? I'm going to implement this, but do you want me to repeat this step? Or are you getting confused? Any feedback can I get?
No, ma'am, it's clear.
All right. Okay. So I'm going to just create a list or numpy array using a range. What should be the shape of that? The shape of this x or shape of y. So I can write x dot shape 0. That will give us the number of elements in x, the number of rows basically. Okay. So once I create this indices, I have to shuffle them. How can I shuffle them? Numpy dot random dot shuffle. This we have seen just now. So we'll be shuffling this indices array. Once we get this shuffled indices, what we'll do is we have to return the shuffled x and y, following the same permutation. Okay. So what we can do is x indices and y indices. This is precisely what we had seen just now. If you want to access some elements from an array, so this is your y array. When you write this thing, you write this 3, 1, 2, 0, you get the elements of y in that order. If you alter this array of indices, let's say you write 0, 1, 2, 3, you will get the elements in that order. So this is basically shuffling. This will shuffle your data. We are yet to divide it into train and test, but this will shuffle. Any doubt in this so far? I'm going to call this function. See, even if you're using sklearn libraries in NLP, I would say these little steps you should be able to code yourself. Okay. Okay. What are we asking? Okay, it is not written in this. I will complete this question. Somehow something is missing. I'm asking the mean of the first 5 elements in y. So the mean of first 5 elements in y, how would we do that? Let's first access the first 5 elements in y, 0, 5, and then the mean of that. So this is what we want to print. Okay. Any doubts so far? Right now that we have shuffled the elements, we have to divide them into train and test, and based on whatever test size we want. The question is, create a function train test bit x, y, and test size. This will be provided always, even in sklearn libraries. The test size is given, and it divides the data, and the value of test size between should be between 0 and 1. So if test size we pass to be 0.2, then 20% data will go to test and 80% will go to train, and so on. So this is what we have to implement. So I'll create a function train test split. So we want to split x and y, and based on test size. This is what we want to create. Now we have already shuffled the data. So we'll use this shuffled data. The test size is given, which is a number between 0 and 1. How do we know how many elements should go to train and how many elements should go to test? How many elements should go to train or test? So test size multiplied by the length of y. Length of y you can write, or you can also write x dot shape 0. Anything is fine. They both are same, right? X dot shape 0 and length of y is also same. Or L dot, sorry, y dot shape is also same. Y dot shape, length of y, x dot shape 0, they all will give you the same thing. I hope this is clear to everyone. Now test size is given to us. This is a number between 0 and 1. When you multiply it with length of y, you get some fraction. Okay, we need to convert that into integer. So whatever this is, these many elements should go to test. So let's say the last elements of this size, okay, this should be the size of the test size. This should go to test. So this is what we are going to code here. So let's see number of train data points. We can write length of y multiplied by test size. These many elements should go to test. You might want to convert it into integer because this is a fraction. So these many elements should go to test. And how many elements should go to train? Length of y minus that very number. So these many elements should go to train data. Now, what will be your x train? From x, you have to fetch some elements. Let's use capital X here. From this x, you have to fetch some elements and they should go to x train. Which elements? Starting from 0, starting from beginning, up to that very number that you have just now identified using this thing. Okay. So what I'll write is x train is equal to train data points. Okay, these elements will go to x train. Now, what will go to x test? The remaining elements, right? This was your x which you are splitting. So initial these many elements went to train, and the last element will go to test. So for that we can write x. So whatever I had given you this example, right? I'll just start from here, and I'll put a colon, which means start from here and go till the end. Simple. Okay. I hope this step is clear to everyone. So this is my x train and x test. The same thing I have to do with y train and y test as well. Okay. So I have to divide the y part as well. Y train will be dividing y with the same strategy, starting up to number of train data points, and y also will be divided. Y test is equal to y will be divided starting from this up to the end. Okay. And this we have to return from this function. Okay. So I'll write return X train, X test, Y train, and Y test. This is the function that we are expected to produce. Now we will call this function so that we get a split data and we can proceed with that. So this function will call and it will give us all these values. We need to pass in the question it is given. The test size should be 0.25. Okay. So we'll pass the test size to be 0.25 and yeah, we're good to go. So we should be now getting our split data in these 4 variables, which we'll proceed with. Whenever we have to do training, we'll use X train, comma Y train. Whenever we have to do testing, we'll use X test, comma Y test. Okay. What are we asking in the question? Output the sum of all Y values settling in Y test. Okay. How can we do that? Y test will have all the values in Y test, and when you sum them up, this should be your answer. Okay. Okay, next question. What are the shapes of all these? Simple question. We can simply just write their shapes. And then by train dot shape, and then by test dot shape. Okay. 332, 10. This one. Yeah. Yeah, C is the correct option. Okay. All right. Let's move on to the next question. Add a dummy feature, that is a column containing all ones, as the first column in X train and X test. Take the transpose of both X train and X test. What are the shapes of these? Now, what do we want to do these, perform these steps? These are just not random steps. These are what are required to perform the linear regression. Okay. Now, I hope this is known to you that this is your X matrix. Whenever you compute the weights, so what is the linear equation that linear regression follows? Let's say y hat, y is the predicted value of y. What do? W1x1 plus W2x2. I mean, let me use F1 because X1, X2 we are using for something else. W1F1 plus W2F2 plus W3F3. These are the feature values, right? Goes up to WDFD. There are D features in the data. And these are the weights that are multiplied with those feature values. But apart from these, there is one more term that is added, W0, and F1 is equal to 1. This W0, we want linear regression to compute. This is also called bias or interceptor. Okay, and this F1, we explicitly take it to be 1, all 1 values. All 1 values we take explicitly. Why do we do this? So in case of 2D, when there is only one feature, what is the equation of line? The line, let's say this is y. The equation of line is mx plus c, normal. This is an equation of a straight line where m is a slope and c is the intercept. Alternatively, you can write it like w1 x1. I'll use f1. w1 x1 f1 plus w0. So we basically convert these m and c to w1 and w0. If there are 2 features, the equation will be w2 f2 plus w1 f1 plus w0, right? And so on. You can generalize it. Now, what I'm trying to emphasize is we add this intercept, we add this extra term. It is equivalent to w01. W01. Which means in order to get this weight value, which is intercept value, we explicitly add this a dummy column. This is called dummy column. We add this one column over here. This is our usual X matrix. Okay. So this is what we are going to do here. Add a dummy feature, that is a column containing all ones in X. Now we know how we can, create a dummy column. Numpy dot ones, right? We have just now seen. What should be the shape of this? Anyone? What should be the size of this numpy dot ones? What should I pass here? The size should be same as the number of rows in X in this matrix. So X dot shape 0. That will give you the number of rows in this matrix X. Okay. So what do we have to do? We have to do it X. Now that we have divided our data into X train and X test, we have to add the dummy column in X train and X test separately. Please note this. So this is also true for any sort of pre-processing that we apply on train and test data. Whatever pre-processing you apply on train data, the same pre-processing you are expected to apply on test data also. So that is something that you should know. Now, since we are adding this column 1 to our train data, we have to add that in our test data also. Okay. So now let's do that. We'll be using this function. How do we add this column 1 here? We'll use numpy dot column stack, right? We have just now seen that. So this will be a column of 1 and this will be our usual matrix. And we'll stack them together using numpy dot column stack. So I'll write numpy dot column stack. What do we stack? So firstly, we'll pass them as a tuple. In the tuple, the first thing will be numpy dot ones itself. Please ask me if there is any doubt that you have. So numpy dot ones. What should be the shape of that one? So first, let's transform our train data. So X train dot shape 0. Okay. Just give me a moment. I'll connect the charger. Just 1 minute. All right, numpy dot column stack. So in this tuple, we are passing what all we want to stack. The second thing to which we want to stack is X train itself. Okay, and whatever we get, we'll assign it back to X train so that our X train is now transformed. Okay, so this is our X train, and similarly, we'll add the dummy column to X test also. So we'll write X test is equal to numpy dot column stack numpy dot ones X test dot shape 0, and the second thing will be X test. We're simply adding that. Some bracket is missing. 1 moment. Oh, sorry, this is a bracket, the square bracket, right? This is also a square bracket. Okay, so if you want to see your X train, so this one, you see, this one is prepended to every data point. Okay, same goes with X test. Now, there's an important thing to note here. When we get data, we need to see what form that data is in. So when we get data from this particular source, or any source for that matter, these are our X1, X2, X3. So basically, this is your X1, this is your X2, this is your X3, this goes up to Xn. And what are the columns? The columns are features, feature 1, feature 2, up to feature D. This is the way we get some data. When you, let's say you load some CSV, you get data in this way, right? You know, you might have seen data in CSV format, probably somewhere. The rows are different data points and the columns are different features, right? That's how we get it. And the same goes with the way we are loading data here also. But if you refer to the lectures, I mean, how we consider what kind of X that we have, the X there is like this. This is our X1, this is X2, this is our Xn. And these are our features, feature 1, feature 2 up to feature D. Now, given this kind of matrix, we came up with that formula, right? W is equal to XX transpose inverse XY. Okay. Now, you can do one of two things. You either alter this formula such that it becomes X transpose X inverse X transpose Y, something like that. Okay. You either transform it like that, or you take a transpose of this. Okay. You take a transpose of this, and this X will become like what we expect, which means the data points will be columns and the rows will be your feature values. Okay. That's why we are asking you take the transpose of both X train and X test. So what we'll do is X train is equal to X train. How do we take transpose? Dot T. Okay. We are simply taking transpose of both X test dot. Now, if you see the shapes, it's transformed. It's the way we want as per our formula that we are going to implement, which means the data points are now in columns. Okay, this is how we have to have it. Now, next question, and we can check the shapes, right? You can do this question easily. Next is compute weights. That uses the closed form formula of linear regression, which I have been writing, XX transpose inverse XY, and returns a weight vector. Okay, we call this function by passing X train and Y train. This is like fitting, right? This is like training the model, computing weights. So when we train the model, that is the point where we compute the weights. That's like training the model. So that's why we will pass the train data to it. Okay, so we'll write this function. What's that? Compute weights. What we pass here? X and Y. For any given data, how do we compute weights? We simply use this formula. This formula, XX transpose inverse XY. And that will be our weights. So XX transpose, let's go step by step. XX transpose, X multiplied at the rate X transpose, X dot P. This is XX transpose. And then you have to take the inverse of that. So we'll use which one? Which function we'll use? Numpy dot linear algebra dot P inverse, right? This function will use. And then we want what? XX transpose inverse and multiplied by XY. Multiplied with X multiplied with Y. Sometimes we forget these at the rates. Please note this. You have to write wherever there is multiplication, you have to write this symbol. Now, this will give you a weight vector. Let's return this. This is what this function should return. Let's now call this function so that we get our weights. So I'll write weights is equal to compute weights using which data? Train data. Please note this. We always find the parameters using train data, and we check those parameters on the test data. This should be it. Let's see what are the weights. These are the weights. Okay. There were how many features? I think 10 features, right? So 1, 2, 3, 4. There are 11 values here. Why 11 values? Because we had explicitly added this 1 here, right? We had explicitly added this 1 over here. So we are now getting 11 weights. And the first weight out of them is the intercept, this value. Okay. What are we asking in the question? As the dummy feature was added as the first column, the first value is the intercept. What is the value of this intercept is what we are asking. So that is 150.80, the first one. There are some weights which are negative, some are positive. That is how it is. Okay. Next question. Write a function mean square error. Now we got some weights. We want to see how much error we are making when we compare our predicted y's with the actual y's. Okay, and that we do using which data? Test data, right? Okay, so we have to write this function mean squared error. How do we compute mean squared error? Basically, it is, so what is the error? The error is, this is the predicted value, this is the actual value, and then you square it up, and then you sum it up, and then you take the mean, right? This is your mean squared error. Now, what is this y hat? Y hat is simply W transpose X, isn't it? Right? Linear combination of um, feature values multiplied with the weights. So y hat is W transpose X. So it becomes W transpose X minus Y square, and then sum it up and then take the average. This is what we have to implement. So mean squared error, let's implement this. Define mean squared error. What do we need to pass? We need to pass X and then Y and then the weights. Using these weights only we'll compute this W transpose X. So W transpose X, let's do that first. So W transpose X we write when, when these are columns. This is column, this is one column. So W1, X1, W2, X2, like that we write, okay? But when these are converted to vectors, W is a vector and this X is a entire feature matrix, then it is actually X transpose W. Okay, when it is, so when you look at the shapes of X, you look at the shape of X, you look at the shape of W. So this is X transpose W, where you are multiplying every data point with the feature vector. Okay, so please note this, when this X and W both are vector form, W is vector, X is a matrix, X transpose W is what will give you the predicted values, y hats. Y hat will be a vector. Okay, so X transpose W is what you'll write. How do you write X transpose? X dot P, and then multiplied with what? Multiplied with W. Okay, minus Y, and then you square it up. So you square this whole thing up. How do you square in Python? Double star you put. This is squaring, and then you sum it up. You sum, so this will give you a vector. You have to sum it up. How do you do that? What function? Numpy dot sum. We just now saw. Numpy dot sum, you sum everything up. And then you take the average of that. 1 by n is what you do. How do you do this? You need to divide with n. What is n? N is the number of data points. Now, in your X matrix that you transformed like this matrix, right? What is n? N is this 1 to n. Okay. This is now in the transformed one, it is X dot shape 1. Okay, which is the number of columns. So that will be your n. X dot shape 1. This is your n. This should be your mean squared error, and we need to return that. Let's see what we get. We have to see the error on train data as well as test data. Okay, use this function, compute train error and test error. So let's first call it on train data. What is the train data? X train and Y train. This will give you train error. Let's store it. This is your train error. Similarly, you can get test error. By passing the test data. W, okay, we are passing W also. So W was what? W was our weights, WTS. We will have to pass that also. Okay, so So this is the train error and this is the test error. Okay. What are we asking here? Yeah, that's what we are asking, the value of test error. This is what we have to output. Now, this was linear regression. Now, next question is compute weights ridge. How do you compute weights in linear regression? I've told you. Now, when it is a ridge regression, your equation is transformed XX transpose plus lambda I inverse XY. Everything else remains the same. The only difference that comes in is you add up this very term. What is this lambda? Lambda is the regularization parameter. What is this I? This is an identity matrix. Okay. So which means if the n is equal to 3, then this is your identity, and then you give some lambda, let's say 0.1, then this matrix will become 0.1. So this will become your this term, which will be added to the covariance matrix XX transpose. Why is it done? This all is done in an attempt to reduce the trace. So you remember the mean squared error was sigma square, and then trace of XX transpose inverse, right? That was it. Inverse. Now, the sigma square is something that is intrinsic to the data in the sense that it is the noise that is present in the data, and we can never learn the noise, right? So the data, which is Y, is generated is like W transpose X plus some noise is added to it with some mean and some standard deviation. So this is some noise which is present in the data. What do we mean by this? See, if the data is something like this, all we can do is we can find the trend line, okay? But these data, so if you're using a linear model, and this is a noise, this is the noise that we are talking about, this very noise, okay? Using a linear model, we can never handle this noise. So this is something we cannot control. I mean, the error that we are getting due to this Gaussian noise that is present in the data, we can never reduce it because this is prevalent in the data. What you can do is probably you can come up with some non-linear model, let's say polynomial model, which it's a very complicated model and takes care of all your data points, and the error is 0. But that is not what we are doing right now. We are building a linear model. And using a linear line, this is what we can cover. So our linear line could be this green one, or it could be this one, or it could be some other linear line. Our motive here is to find the best linear line. But the error that is coming due to this very term, that can never be handled. So we will not be looking at it. So so getting back, the sigma square is coming from here, which we cannot reduce. In order to reduce this mean squared error, we can reduce this. How can we reduce this? What is trace? Trace is the sum of the eigenvalues. Okay, and if let's say lambda 1, lambda 2, and lambda d are the eigenvalues of, let's say, XX transpose, what will be the eigenvalues of XX transpose inverse? Anyone? Anyone?
1 by
The
lambda.
reciprocal of those.
Correct. Where are we? Yeah. Here in the mean squared error term, we have XX transpose inverse. So we are interested in the eigenvalues of XX transpose inverse which will be 1 by lambda 1, 1 by lambda 2, and up to 1 by lambda d. Now, what will be the trace of that? The sum of these values. The sum of these values. So this is what we are interested in, and we will try to minimize it. Our motive is to minimize this. Okay. Now, if lambda i's are the eigenvalues of XX transpose, then what will be the eigenvalues of XX transpose plus lambda I? If lambda i's, which is lambda 1, lambda 2, lambda d, up to lambda d are the eigenvalues of XX transpose, what will be the eigenvalues of XX transpose plus lambda I? Lambda i's
Lambda will be
plus
added.
lambda. Lambda will be added. Very good. Okay. So these will be the eigenvalues of this very matrix, which means if we add this term, our eigenvalues are increasing. Now, this is mean squared error, right? We need to minimize this. We need to minimize this term. Hence, we need to minimize this term. When would this term be minimized? When these will be minimized. Sorry, when would this term be minimized? When these are increased, right? These are in denominator. So in order to minimize this, you might want to maximize this, increase these value. So that is what we are doing here. We are adding another term here. This plus lambda is, when this plus lambda is added here, plus lambda, the denominator increases and hence the whole term reduces, and hence this whole term reduces, and hence the mean squared error reduces. Okay, so getting back, this is our analytical equation for ridge regression. Again, you can use gradient descent. Getting back, again, there are two ways. You can use either this equation that I've just now mentioned directly to get the weights, but if data is huge, you'll not use that once again. If the data is huge, if the D is high, you might want to get back to gradient descent. Okay, so here we will be now implementing this very equation to get the weights as per ridge regression, and we'll see how they vary with respect to linear regression. Okay, now, so we'll write another function which is compute weights ridge. Okay, this function will write, and x and y. There's one thing missing here. The regularization strength also it expects, right? How much lambda value, that also should be there. So let's write the function weights, let's say, as per ridge. Okay, we want to pass x and y and this L for lambda. Okay, the same equation I'm going to write. What should I write? X transpose x multiplied x transpose plus one moment, x transpose plus lambda, right? What is lambda? Lambda is L. L into I. How do we get I? How do we get I?
np dot I.
Yeah, numpy dot EYE. What should be the shape of this I? The shape of this I should be this same as the shape of XX transpose, right? The shape of XX transpose, the number of rows will be same as the number of rows in X, right? XX transpose, let's say this is 3 cross 3, let's say this is be 3 cross 3 and the resultant is 3 cross 3. So the number of rows will be same as the number of rows in X. So X dot shape 0 is what we are after. Okay, numpy dot I, what? X dot shape 0. Okay, this is your lambda into I, and we want, what do we want? We want the inverse of this. Okay, I'm putting everything in one bracket, and then I am writing numpy dot linear algebra dot P inverse. Okay, I hope the brackets are correct. So this is our first part, and then that should be multiplied with what? X multiplied with y. Okay. Let's cross check. X transpose plus lambda I x dot shape 0. Brackets are fine. You take the inverse of this and multiply it with x. We need to return this. This should be our weights as per ridge. Let's see what we get. So let's say I write weights as per ridge is equal to weights, which function I'll call. I'll call this function on which data? I'll call on train data. Okay. Call this function by using x train, y train, and point 3 as the regularization strength. So I'll pass x train Y train, and 0.3 as a regularization value. Let's see what we got. This is what we got. Let me round this up. These are the weights that we are now getting. If you see the weights that we were getting earlier, let me write here only for the sake of comparison. That was weights, right? Yeah, weights. Let me write it here. These are the weights that we were getting earlier. And these are the weights that we are getting now after we apply this regularization. Okay. If you see this weight, earlier this was minus 37.5, now it is 1.2. So in general, most of the weights will be reduced. Sometimes there might be one or two weights which might increase because there are two terms, right? In the loss function. So this is the equation of weights. Please note, this is the equation of weights. If you talk about the loss function, what is the loss function in linear regression? Anyone? What is the loss function in linear regression? Mean squared error only, right? Y hat minus y, and then square it up and then sum it up. Okay. What is y hat? This is your loss function, linear regression. When ridge comes in, what extra thing that comes up is lambda, and then we want to minimize the squares of weights, the L2 norm of the weights. Okay, this is what we want to minimize. So basically, we are trying to bring the weight values down. So in case of ridge, we are not only trying to minimize this sum of squared errors, we are also trying to minimize this. We are trying to minimize this whole thing. So as a result of this, the weights are reduced to smaller values. Of course, depending on this value of lambda. This lambda is actually sort of penalty that we apply for weights being higher. Let's say lambda is equal to, we have taken lambda to be 0.3. Let's say I take 2.5, which means I'm giving more penalty for higher weights. So more this, so this is also called regularization strength. More this lambda, more the penalty, and hence lesser will be the weights. Okay. Please note these weight values are being used here as well. So when you reduce this, there is an effect on this also. So accordingly, in total, we have to minimize this whole term. So the general effect would be that the weights will be reduced. So let us try to visualize this also, so that we get to see how weights will reduce as you vary the regularization strength. The next question asks about the train error and test error. There's one more thing that I would like to highlight here. Let's first compute the train and test errors, and then I'll speak about that. So using these ridge weights, what will be the error? Let's say train error. I'll call the function mean squared error, and what will I pass? I'll pass the train data, x train and then y train, and as weights I'll be passing weights underscore r. This is the ridge weights. This is the train error. Let me also see how much is the test error. I'll now be passing test data, x test and y test. Same weights. 3058 and 2959. Now we're asking here, what is the absolute difference between them? By dot absolute, the difference will be train error minus test error. 99 is the difference. Okay. If you see the difference here, I'll just because the variable names are same, I'll just write the statement here. No, train error is changed, right? So what I'm trying to say is that the difference between these two is high. So there's something called overfitting. There's something called overfitting. How do you check whether the model is overfitting or not? If the train error is, so this is error only, right? So in general, overfitting happens when the model is performing well on train data but not performing well on test data. Okay, the difference between train error and test error is huge. That's when overfitting happens, and that is a situation where regularization is applied. Okay, when you reduce the weights, then overfitting is reduced. So you might learn it later on when polynomial regression comes in. So in polynomial regression, you do not fit a straight line, you will fit some polynomial of the given feature values. So if your data is not linear, you obviously cannot use a linear regression. You'll use some polynomial, let's say degree 2, degree 3, or some polynomial you'll use. So as the degrees are increased, the model is likely to overfit the data, something like this. And if you keep increasing the degrees, you can fit any data. But it is possible that if the degree is, let's say, 50, let's say it's very high, let's say degree is 15, you are able to fit your data and hence your train error is 0. It might be possible. Train error is 0. But when the test data comes in, the data will not be same, right? Because it will be actually a different data. And your model has learned the noise also in the data, and hence the train error is 0. So when test data comes, it is not exactly same. So there is a huge test error. This is precisely the case of overfitting. And in overfitting, only we apply ridge regression, or let's say lasso regression. And what it tries to do is it reduces the weights, and hence the model will become simpler. If earlier it was this red line, now it will become something like this, so that it captures the basic patterns in the data and doesn't learn the noise. Okay, so probably polynomial regression will be covered, and then these things will be clear. But for now, let me visualize the difference between the weights that you get from linear regression and when you apply ridge regression. Okay, so in the question, we are asking that regularization strength to be varied between 0 to 5, and then keep a record of the weight vectors that we obtain, and then plot them. All right, so I hope you all are good in visualization. So we have to vary the values of this L, this strength that we had used to be 0.3. Let us use different values for this L and this, and then call this function weights ridge, and then keep a record of the weights that we get. So what we'll do is we'll start a loop for L in, we want 10 values between 0 and 5. Okay, which means we know how many values we want. So we'll use numpy dot linspace starting from 0 up to 5, and we want 10 values. Okay, we'll write these values of lambda, and we'll call which function? Weights ridge. Okay. And what data? The data will be same, train data, X train and Y train, and we'll pass this L value, and we'll store these weights that we'll obtain in some variable. So these are our weights that we'll be getting. We need to keep a record of these weights. So let's create a list where we'll be keeping these weights. So I'll write weights dot append. These weights I'll keep here. Okay, weights dot append weights are. Plot the sum of these weights. See, when weights are reduced, the sums are also reduced, right? So we are also keeping track of another thing, the sums of weights, so that we can also see that how that varies with respect to lambda. So weight sums is another list that we'll be maintaining. So I'll write weights sums dot append. What do you want to append? The sum of this weight. So I'll write weights r dot sum. That will give us the sum of these weights, and they should be appended. Okay. Let's see what we got. So basically, we should get two lists, weights. So these are the different weights that we get with respect to different lambda values, and weight sums also. Let's check. These are the sums of all the weights that we are getting. Okay, you might want to probably visualize. Matplotlib is already imported. So I'll write plt.plot. What should be on the x-axis? The x-axis should have the lambda value. So I'll simply write numpy.linspace. The same thing I'll write here. 0 to 5 and 10 values in between. This is the x-axis. The y-axis is weights. Okay. Let's have some marker and some line. So this is what is happening. So on the x-axis we have weights, the lambda values. Right? Initially, the lambda is small, which means regularization strength is small. So these are the weights that we are getting. When the lambda is increased, the weights are reduced. As you can see, gradually the weights are, so this is 0. Okay, gradually the weights are reducing. Let's also plot the sums of these weights. Plot x-axis remains the same. Weights sums, right? Sums. So the sum of weights is reducing, as you can see. This is the effect of regularization. Okay. Any doubts that you have at this point? Are you writing something in chat? Okay. Yeah. Any doubt that you have in this?
Ma'am, one doubt here. So, at what ma'am value of penalty here, like we can conclude like that will harm
Okay.
our learning?
Yeah. So there's cross validation, right? Cross validation. So this lambda is actually a hyperparameter. So anybody would like to tell me what is the difference between parameter and hyperparameter? Anyone?
Hyperparameter which you tune yourself, and parameter which you find out to the.
Correct. Not you. The model will find out.
Yes.
Okay.
Yes.
Correct. So that's an important distinction and that everybody should know. So parameters are those values which the model finds out for you, and hyperparameters are those values that you need to pass to the model before the model training starts. So as an example, in linear regression, the weights, the W0, W1, W2, all these weights, these are, so can you tell me these are parameters or hyperparameters?
Parameters.
Anyone?
Parameter.
Right. These are parameters because these are provided to us by the model. Okay. But before the model starts, it expects us to provide this value of lambda. Lambda is a regularization strength. So we need to give this value. So k-means is done, right? So in k-means, can anybody tell me what is the hyperparameter in k-means?
You provide the number of clusters.
Right, this k. So before k-means starts any learning from the model, from the data, This k it expects us to provide. So in k means k is a hyperparameter. Well, getting back here, this lambda is a hyperparameter, the regularization strength. So how do we find the values of hyperparameters? One way is you try out different possible values yourself manually. Okay. Second is cross validation. Well, in sklearn, if those who are doing MLP, there are different libraries that do it for us, like grid search CV is there, grid search CV is there, randomized search CV is there. These libraries try out different parameter values and then tell us which of these values is working the best on the given data. And they give us something like best parameters, best params. So this lambda can be found using such libraries. So internally, what these libraries do is cross-validation itself that has been explained in the lectures. So I've been telling you that given the data, we will be dividing into train and test, right? So this data will be train and this data will be test. But apart from this, there is one more division that happens. In the train data itself, you'll keep some more data aside and you call it validation data. So if this was 20% and this whole thing was 80%, probably 20% again you'll keep, and 60% is what you will train your data on, and you will check or validate the results of that model on this validation set, validation data. And you will see whether it's working fine or not, because test data is actually not touched until the model is done with the training. It's accessed in the end after the model has been trained. But this lambda is something that we want to know what is the good value of lambda during the model training itself. So we keep some of the data from training itself aside. Now, it may be possible that you got some bad data here and some good data here, or vice versa. You got some good data here you got some bad data here, because you are randomly choosing. It is possible. So in order to avoid that, you perform cross validation. And what is that? I hope this is this clear, or do you want me to cover that cross validation?
That is clear, ma'am.
All right. So we divide into k-fold cross validation. You divide into k parts and you check different kinds of data and hence find the best value of lambda. All right. Is that clear? Whoever had asked the question.
Yeah, yes, ma'am. Ma'am, one more doubt here. In that mean square error, we do sigma square trace of x transpose inverse. Like, how did this come, ma'am?
Yeah, that. One moment. Yeah, so this is basically expanded. So do you want a derivation of this? I can actually provide that. Probably do one thing. You drop a message on Discourse and I'll answer it there. Okay.
Okay, sure.
So there's a whole derivation behind this. If you want to understand how this is done, probably we can take it there. Okay.
Yeah, sure.
All right. Others, any doubts? Anything that you? So I hope you will do this now that you have seen it in detail. Please try it out. And any other doubt that you have before we leave?
Ma'am, one general question.
Yeah.
Generally in Excel sheet, what I was doing for plotting this trend line, I was by default I was using power 2. So
okay.
So what is the best practice actually? I mean, I never used a linear.
I see.
So I always use a 2, 3. I mean,
this power. Yeah. So again, this is a hyperparameter. This power is the degree that we provide in polynomial regression. Okay.
Yeah.
So generally we use linear regression, but if we know that the data is not linear, we might want to try out different powers to fit our data better. So this degree, we don't know, right? We don't know which degree will be good, 2, 3, 4, whatever. So we try out different values of degrees. Okay. Now, when you increase the degree, like I'm repeating myself, I just now had told, when you increase the degree, your data will be fit better. Your data will be fitted better when you increase the value of degree, because let me share my screen again, because you might get when you increase the degree, you might get a very complicated polynomial, and that will be able to learn little details in your data. uh, you can try it out. It's very simple to do in code as well. So when you increase the degree, your error will reduce, because these little details, it will become a very complicated curve. Okay. So when we do this, the error reduces on trained data, but on test data the error doesn't reduce, because in test data the noise will be different, right? This is n, this is a normal distribution, and this is the variance. It's generated randomly. So whatever randomly got generated in the trained data was learned by your model, but whatever randomly will get generated in the test data will be different, and your model will not be able to fit that. Okay, so that is why on trained data you will get low error or zero error in the extreme case, and in test data you'll get more error. That is why what you do, you apply regularization. Okay, so you can increase the degree to, let's say, 10, but if your model is regularized with some lambda provided, this lambda will not let the weights of the higher powers increase. What do we mean by D? So uh, let's say there is one feature, F1, let's say there is one feature. Okay, what will be the kind of equation that you'll get? Y hat is equal to W naught plus W1 F1, right? This is linear equation. If you apply degree 2 polynomial, the data will be transformed such that F1 is there, this is constant, F1 square, this will come in. So the weights will be like W naught plus W1 F1 plus W2 F1 square. Now imagine that D is equal to 10 is there, then it will be like, the data will be transformed like F1 F1 square up to F1 to the power 10. And the Y hat will be W naught plus W1 F1 plus W2 F1 square plus W10 F1 to the power 10. Now W10 is the weight of the 10th power of F1. This is the huge power of F1. So if the data is actually not that complicated, that a degree 10 polynomial is suitable for that, you might not want this weight to be high. If this weight is 0, we are good. If this weight is like 0.1, that is also fine. But if this weight is like 10, let's say, even a little change in F1 will make the model work in a weird manner, right? I hope you're able to understand that. So our motive will be to reduce these weights, these higher power weights. So when these weights are reduced by using regularization, our model will tend to be simpler and not as complex as it would be in the absence of regularization. Well, getting back to your question, what should be the right degree that you should use, right? So, so in Excel, you can only do hit and trial. But then higher degrees will, like I said, will overfit your model. So you should come back to your code and should see what, using cross validation, what is a good value of this degree. Okay.
Okay.
Yeah, cross validation is what you should implement. If you want to do it from scratch, that we need to see. Probably we can add these cross validation questions from scratch in some of the exercises. But for now, you can use sklearn for this purpose. In sklearn, there are some libraries that you can make use of. You can directly use grid search CV and randomized search CV also. Okay.
Okay.
You can ask me if you were not able to do it. It's straightforward, actually. It's very simple. Maybe you can try in the next live session. You can ask me. All right. Anything else? Any other doubts? Okay, I hope that was clear. Please try out these programming assignments as well. And the deadline will be extended to 23rd. All right, great.
Deadline extended, ma'am. Thank you.
You got the mail?
I checked in the
You
Oh,
checked
that.
it, you got it? All right, great. So do it comfortably, and yeah, take care for the festive season.
Yeah. Thanks
Uh,
a lot, ma'am.
all the best. Bye. Yeah, thanks. Bye.
Thank you, ma'am.
Excuse me, ma'am.